team. Welcome to the February 2014 Electromagnetics Conference. We've recently decided to break into the dielectric resonator antenna market. Yasser, will you give us some background on what we'll be dealing with?
Now I'll be talking about the brief history of the dielectric resonator antenna. For many years, the dielectric resonator has been the primary use of microwave circuits. Some examples are the oscillator and filter, where the dielectric resonator is normally made of high, primitive material. When the dielectric resonator antenna was first presented to the general public, it was not widely accepted by many people. It was not accepted till 1983 when an original paper was published talking about the cylindrical dielectric resonator antenna. Dielectric resonator antennas are made out of low-cost dielectric material and is a potential candidate for high-frequency application for its high radiation efficiency. Its inherent wideband nature, lightweight, competitive in size, ease of fabrication, low cost of dielectric resonator antennas is very attractive for potential users. Over the last decade, various bandwidth enhancement techniques have been reported in literature on dielectric resonator antennas, DRA for short. The DRA has been constantly compared to the microstrip antenna, but there have been many problems with the microstrip antenna compared to the DRAs. The major difference between the microstrip antenna and the DRA is that the DRA has a much wider impedance bandwidth. The DRA radiates through the whole dielectric resonator antenna except through the ground surface part, but the microstrip antenna radiates only through the narrow radiation slots. Now I'll be talking about the problems with the microstrip antenna. The microstrip antenna has a narrow bandwidth for electricity than substance. The higher the frequency, the results will be it will have loss for ohmic loss and electricity thicker substance which supports the surface wave and decrease the radiation efficiency. Now I'll be talking about the idea of how the dielectric resonator or the DRA came to be. The DRA enhances the leaker or radiation to convert energy storage devices into antennas. Similar geometry to a circular microstrip but with the conducting patch. It can choose dimensions and dielectric constants to enhance radiation. Now I'll be talking about the problems with the microstrip antenna. The first problem is that it has a narrow bandwidth for electricity than substance. The second problem is that the higher the frequency, it will result in two minor problems. It will have more ohmic loss, also it will have electricity thicker substance which supports the surface's waves and decreased radiation efficiency. So now I will be talking about the idea of how the dielectric antenna came to be. So the first major point is the dielectric resonator antenna enhances the leaker or radiation to convert energy storage device into an antenna. The second thing is it has a similar geometry to circular microstrip but with a conducting patch. And the third major idea is it can choose a dimension and dielectric constant to enhance its radiation. So the dielectric resonator antenna or DRA can be used in multiple situations, and it also has future applications. So the first future application is the dielectric resonator is an idea ahead of its time. As operating frequencies continue to rise throughout the years, dielectric resonator antennas will become much more useful. Another thing is dielectric antennas need to develop integration techniques for fabrication. Dielectric antennas someday may be as common as microstrip antennas.
Interesting. AJ, how are we going to put these things together?
I'll now be talking about the fabrication process of dielectric resonator antennas. The fabrication process is not too complicated and does not make use of rare materials. They can be built entirely out of ceramic, which is especially good for higher frequency waves that are still in the microwave or millimeter range. Since the metal is less efficient at those frequencies, this is a good thing. Furthermore, ceramics have a high dielectric constant, which allows manufacturers to make them relatively compact. It is usually trivial to find ceramics with a wide range of dielectric constants, making both the size and targeted wavelength easy to customize. Choosing the geometry and material are the two most important design decisions before the fabrication process can begin. In traditional dielectric design, there is simply a block of ceramic material that acts as a resonator mounted on a metal ground plane, where the dielectric constant of the ceramic corresponds to the targeted wavelength. In general, higher frequency waves require a higher dielectric constant for the device to remain compact. In the case of designs without complex geometries or very small components, the ceramic may simply be machined into shape. This involves carving some standard-sized block of ceramic into the required shape with high-speed machining tools. Antenna designs with smaller feature sizes may have to use other means depending on the materials required. As an example, a reflective array antenna may have sub-millimeter strips of conductive metal acting as a waveguide embedded around small dielectric cells. The dielectric may still be machined, but the metal must now be deposited onto the surface using more advanced techniques, such as evaporation. In this technique, the metal is evaporated in a vacuum alongside the dielectric, which acts as the substrate. Eventually, a thin film of metal is deposited onto the surface of the already machined dielectric. Overall, the manufacture of dielectric resonator antennas is not complicated, although newer, specialized, or more compact designs may call for features that require special consideration during manufacture. For simpler designs, all components can be mass-produced and are not difficult to obtain or manufacture, which is an advantage of the technology.
Thank you, AJ. Mafuser, how we looking on paper?
So dielectric resonator antennas are ceramic resonators that radiate energy into space when excited appropriately. Besides application in antennas, these ceramic resonators are used in microwave circuits in areas such as filter and combiner applications. They are usually encased in a casing to prevent energy lost through radiation when used as such devices. DRAs are known for their Q factor and temperature stability. Q factor is a dimensionless parameter that describes how underdamped an oscillator or resonator is. For dielectric resonator antennas, the Q factor can range from 20 to 5,000. The relative dielectric resonator constant, which is epsilon r, for commercially available resonators can range up to about 90, and the temperature coefficients of resonant frequency can range from about -6 to 4 parts per meters per degree Celsius. The dielectric resonator antennas contain antennas near field and therefore prevents it from interfering with other nearby antennas or circuits, making it suitable for miniature and compact equipments. DRAs are one of the most recent progressions in antenna technology. They're taking their place on par among the more common antennas such as wire and reflectors. DRAs come in many different shapes and sizes, the most common being cylindrical. A cylindrical DRA has a radius A and height h, and the ratio of radius over height is usually between 0.5 and 4. The DRA usually sits on top of a ground plane and is excited using a probe or aperture. DRAs can resonate at many different modes. For example, the cylindrical DRAs are analyzed and indexed in a similar manner as that of the dielectric waveguide. DRAs have attracted the antenna designers in microwave and millimeter waveband due to its features like high radiation efficiency, its lightweight, small size, low profile, low temperature coefficient of frequency, zero conductor losses, and suitable scale in microwave band. Dielectric resonators of low-loss dielectric material having dielectric constants as 10, less than epsilon r, less than 100, are ideally suitable for antenna applications, so that a compromise can be made between size, operating frequency, and other antenna radiation characteristics. These antennas can also be easily integrated into portable communication devices. A DRA element is placed on a ground plane and a short electric probe is penetrating into the resonator. The probe is located off the center, close to the perimeter of the resonator. The radiation occurs mainly in the broadside direction and it is linearly polarized. A lot of research has been devoted to the study of DRAs in the last decade, and the results show that dielectric blocks of cylindrical, rectangular parallelepiped, hemispherical, half-split cylindrical, and equilateral triangular shapes can be designed to radiate efficiency through proper choices of feed location and dimensions. Different types of feeding structures such as coaxial probes, microstrip lines, microstrip fed aperture, and coplanar waveguides have been proposed. DRAs are a recent development, which means there's still a lot more room for development. However, the amount of papers that have been published for DRAs is still limited.
Good. Now, does anyone know how we're going to measure these things? Can someone get Ali on the wire from Dubai, please?
They are both invisible, so it is harder to measure than regular everyday measurements. They exist everywhere on the Earth and have many measuring instruments. Radiation is usually made up of frequency, wavelength, and its strength. In practice, many instruments that are used are overlapped. That is not a bad thing, because the more instruments that are used to measure, the more accurate the results will be for dielectric resonators. One of the more common measurement tools is called the field strength meter. It is very helpful for any type of antenna development, experiment, or adjustment antenna comparison, and useful for making and observing radiation patterns of antennas. It is able to measure any electromagnetic wave frequencies and wavelength, and it is designed to accommodate an external antenna either directly or via a transmission line. As for the electromagnetic field measurements, using sensor and probes such as EMF meters commonly do those. These probes have different characteristics and have to prevent coupling and reflection to get accurate results. There are two types of EMF measurements. The first type is called broadband measurements using a broadband probe. That device is made with 3 independent diode detectors and senses signals of frequencies. The other type of measurement is frequency selective measurements, which include a field antenna and frequency receiver. This is very helpful because it measures frequencies all over the spectrum. As for antenna specifications, many designers look for radiated test data without understanding what they are exactly looking for. But what they're looking for is a radio frequency component. Specifications are very important in order for the dielectric resonator antenna to work, one of which is the impedance of the antenna. The impedance is the resistance and reactance that appear at terminals of dielectric resonator antennas. Antenna impedance relates the voltage to the current at the input of the antenna and is known as resonator if it is real input impedance. Another specification is the voltage standing wave ratio, otherwise known as VSWR, which is the measurement which is how good of a match dielectric antenna is the source impedance. The measurement is determined by evaluating the voltage wave coming toward the load and the wave leaving the load. Another specification is the measurement towards energy, which is the easiest way to measure the antenna's performance. The 3 specifications that are most involved in energy are efficiency, directivity, and gain. Efficiency is the amount of energy that gets radiated in free space rather than wasted energy. Directivity measures the greatness of peak radiated power density, and that's in the direction of gain and the directivity of the antenna reduced by losses of the antenna. It is basically the product of directivity and efficiency, and is the most important to measure the dielectric antenna's performance.
All right, Ali. Thanks for waking up for us. Go back to bed. Preet, can you tell me about the applications of our antennas?
Alright, I'll be covering the application of dielectric resonator. So, the dielectric resonator is mainly used for radio waves and microwaves. It's known for its mass productivity and low cost. It also comes in different shapes and sizes depending on the product it's being used for, and also different frequencies. Manufacturers sell in different series. It all goes all the way from 2000 to 3000, and it depends on the temperature, the Q factor, and the cost of these things. The main use of the dielectric resonator is a dielectric resonator oscillator. So the main use of dielectric resonator is dielectric resonator oscillator, and it's mainly used to control the frequency of radio waves generated from a source. Now this source pretty much is an oscillator which converts direct current to the alternating current. It produces signal from 100 kilohertz to 100 gigahertz. Another use of dielectric resonator is microwave filters. This is a device which passes microwaves of certain frequency in a transmission line. Transmission line, which is a specialized cable which carries alternating current while absorbing or rejecting some currencies. There are many types of microwave filters that are used in the industry. These are designed to operate around some same frequency as a dielectric resonator, which is around 800 megahertz to 50 gigahertz. The picture that you see on your screen right now is another type of microwave filter which operates around 40 to 960 megahertz of frequency. This is also mainly used part in the industry for dielectric resonators. Another type of dielectric resonator is a dielectric resonator antenna, which mostly comes in the shape of long disc, and it's used at the microwave frequencies. As you guys can see in the picture, that the blue part is where all the radio waves pass through and pretty much radiate through the space. And this blue part is mounted on a metal surface. The reason this is better than other products is because this has less metal parts, which has lower loss of energy and also more efficiency. Another major commercial use of dielectric resonators are motion detectors. Now these motion detectors are used because they have high frequency detectors. They give you accurate results, and there's a long detection range. And they're mostly used in automotive, collision avoidance. Another use for dielectric resonators are radar detectors, which are mostly used by the weather station. These are used because to increase the frequency, to increase the accuracy of the speed and the distance of the object. This also ties into GPS, which also use the dielectric resonators. Dielectric resonators are not only limited to industrial sector, they're also used by the military.
All right, thank you, Preet. Great work, guys. I think we'll definitely be able to break some ground in the coming months. We'll convene again once we've made some more progress. Everyone have a safe and happy reading week, and remember to study hard for 2FH3.